Welcome all of you. I'm Rosalind Mishra and today we will be dealing with Pharmaceutical Inorganic Chemistry. Alright. In Pharmaceutical Inorganic Chemistry, this is our continuation class. We were discussing about Unit 4. Okay. In our previous classes, we had understood about expectorants. Today we will be dealing with the next topic of our Unit 4, which is Emetics. Alright. So now moving on further. Under Emetics, we are expected to learn two major drugs, which is copper sulphate and sodium potassium tartarate. Copper sulphate and sodium potassium tartarate. Alright. So now moving on further, without wasting much time, let us learn what is emetics. What are emetics? Emetics are agents that cause vomiting. They are the agents that are responsible for vomiting. There are two general classes of emetics. Alright. There are two major or general classes for emetics. One acts on the chemoreceptor trigger zone. The first class of emetics acts on the CTZ. Please remember, please pay attention. Please pay attention here all of you. The first class of emetics which is acts on chemoreceptor trigger zone. They act on the CTZ or chemoreceptor trigger zone. This zone or the chemoreceptor trigger zone or the CTZ is located on the medulla and the second acts on the stomach itself. Okay. So, emetics, they act on two major areas. Number one, the CTZ, also known as chemoreceptor trigger zone, and the second class of emetics act on the stomach itself. Alright. Now, moving on further. What is this chemoreceptor trigger zone? Before understanding the category of drugs, first of all, we need to understand these two areas at which our emetics work. Number one is the chemoreceptor trigger zone. It is an area of the medulla oblongata that receives input from blood-borne drugs or hormones and communicates with other structures in the vomiting center to initiate vomiting. See, this chemoreceptor trigger zone is the part of the medulla which is uncovered. Okay, it is uncovered. It accepts it. There are certain blood-borne drugs or hormones which signals this CTZ to initiate vomiting. Okay, CTZ communicates to the vomiting center to initiate vomiting after being stimulated by certain drugs and hormones. Okay. So, this is about the CTZ or the chemoreceptor trigger zone in layman terms or in easier words. This CTZ is located within the area postrema. It is located within the area postrema, which is on the floor of the fourth ventricle and is outside of the blood-brain barrier. It lies outside the blood-brain barrier. So, it is basically uncovered area. It is also a part of the vomiting center itself. It is also a part of the vomiting center. Now, emetics such as syrup of ipecac have been used in emergent cases of poisoning because they induce forceful emptying of the stomach. Okay. So, now moving on further. How is this area or how is this CTZ stimulated? See, CTZ is stimulated in the following way. Tactile stimulation of the back of the throat produces a reflex to get rid of something that is too big or too irritating to be swallowed. Okay. So, tactile stimulation of the back of the throat produces a reflex to get rid of this big or irritating substances. that could not be swallowed. Next, excessive stomach distension also triggers the CTZ. Excessive bloating or inflation, distension of the stomach also leads to stimulation of the CTZ. Increasing intracranial pressure by direct stimulation. When the pressure inside the cranium is increased, then it directly stimulates CTZ, or it stimulates the vomiting center. Stimulation of the vestibular receptor lying inside our ears. When the vestibular receptors are stimulated, these vestibular receptors are responsible for motion, head position and spatial orientation. Alright, this horizontal, vertical, spatial orientation is determined by vestibular receptors. When these vestibular receptors are stimulated in the inner ear, intense pain fibers are stimulated, which in turn stimulates the CTZ. Direct stimulation of various chemicals. Direct stimulation of various chemicals, including fumes, certain drugs and debris from cellular death, also leads to vomiting. Okay, that is direct stimulation of the CTZ by chemical substances, fumes, cellular debris or odor of bad quality leads to stimulation of this vomiting center. CTZ is stimulated by several different processes and initiates a complex series of response that first prepare the system for vomiting and then causes a strong backward peristalsis from the stomach. It forms a strong backward peristalsis to rid the stomach of its contents. Okay. So what happens? First, the CTZ is stimulated, alright, by different responses. It could be drugs, it could be fumes, it could be cellular debris, it could be due to vestibular stimulation, stimulation of vestibular receptors, it could be direct stimulation through intracranial pressure, it could be excessive stomach distension, or it could be something too big or irritant upon which has been swallowed by mistake. All these reactions could stimulate the CTZ center. What happens after that? What happens once the CTZ is stimulated or the chemoreceptor trigger zone is stimulated? The different processes, several different processes gets initiated. Alright, these form a series of complex responses that first prepare the system for vomiting. They cause a strong peristalsis, that is outward reverse motion of the food or of the content which is present in our stomach, hence it gets expelled out. Now, there are several neurotransmitters for emesis. Alright, what are these hormones which are responsible for emesis or which are responsible to cause vomiting? Most important, acetylcholine. Acetylcholine, muscarinic receptors are involved in peristalsis, micturition, bronchoconstriction and several other parasympathetic responses. Alright, acetylcholine acts on these receptors. What does muscarinic receptor do? They cause bronchoconstriction, they are involved in peristalsis, micturition and several other parasympathetic reactions. Alright, so acetylcholine stimulates these muscarinic receptors. So what are the neurotransmitters of emesis? Number 1, acetylcholine. Number 1, acetylcholine. Alright, followed by substance P. Followed by substance P, which acts on NK1 receptors. They act on NK1 receptors. These NK1 are the main receptors for tachykinin family of peptides. Substance P is the major mammalian ligand which are present in brain regions involved in the vomiting reflex. Alright. So, substance P is the ligand for these category of peptides which belong to the family of tachykinins. Clear all of you? Acetylcholine is the ligand for our muscarinic receptors. Similarly, substance P is the ligand for NK1 receptors. What are these NK1 receptors? These belong to the family of peptides. These belong to the family of peptides or tachykinins. The CRTZ is also stimulated by dopamine. It is also stimulated by dopamine. Alright, dopamine is the ligand for D2 receptors. The CTZ or the chemoreceptor trigger zone is also stimulated by alpha adrenergic drugs. It is also stimulated by alpha adrenergic drugs. Serotonin, acetylcholine, enkephalins and histamines. These are all other neurotransmitters for emesis. These are other neurotransmitters for emesis. Now, discussing further, alpha adrenergic receptors in the chemoreceptor trigger zone are important in inducing emesis. Okay, alpha adrenergic receptors in the chemoreceptor trigger zone are important in inducing emesis in cats. Alpha 2 adrenergic agonists, example xylazine, are more potent emetics in cats. Followed by 5-HT1A antagonist, example buspirone, and alpha 2 adrenergic antagonist, example acepromazine, yohimbine and mirtazapine. They suppress vomiting in cats. Okay, so these are the anti-emetic agents. Xylazine, they are potent emetics in cats, whereas these agents, they suppress the vomiting in cats. What are the adverse effects of emesis? Emetics are contraindicated in patients that are hypoxic. In cases of hypoxia, emetics are not allowed because the peristalsis movement, the upward peristalsis movement, which helps in removing out the food material which is present in our gastric tract, requires a lot of energy. So in cases of hypoxic patients, it should not be used. It should not be used in patients who have breathlessness condition, who are the patients who have difficulty in breathing, which is also known as dyspneic patients. Even in such people, emetics should be avoided. People who are unable to swallow, hypovolemic people, that is what is meant by hypovolemia. Well, hypovolemia is a condition in which 1/5 of the fluid loss is seen in a person. If a person loses 20% of the fluid in the form of blood or any other form, then this condition is known as hypovolemia. So in such patients, emetics should be avoided. Alright. Emetics should not be given to animals which have ingested strong acids or alkali, because the contents of the vomitus may cause further damage to the esophageal, pharyngeal or the oral tissues. Clear all of you? If accidentally someone ingests strong acid or alkali, we should not regurgitate it. We should not try to regurgitate it back, because these strong compounds may damage the esophageal tract or the oral cavity or the pharyngeal tissues. Alright? So, these are the cases in which emetics should be avoided. Moving on further. Given the risk of aspiration, emetics should not be given after ingestion of petroleum or related compounds, because the risk of subsequent aspiration overweighs the potential toxicity. Okay. Now we will be looking into classification of emetics. Emetics are divided into three major classes. emetics are divided into three major classes. What are those? Number one, stimulation of CTZ, emetics which act by stimulating chemoreceptor trigger zone. Alright. So, example, apomorphine and morphine. Morphine and apomorphine. Second category, emetics that act by irritating the gastric mucosa. Okay, these drugs act by irritating the gastric mucosa. Example, mustard and sodium chloride. Example, mustard and sodium chloride. Next, emetics that act by both stimulant and irritant effect. That is, these are the category of drugs that stimulate the CTZ center as well as they cause gastric irritation. Okay, so these drugs act both ways, by irritating the gastric mucosa and stimulating the CTZ as well. So, examples of such drugs, ipecacuanha and digitalis. Ipecacuanha and digitalis. So, these are the two drugs that act by stimulating the gastric mucosa or irritating the gastric mucosa and stimulating the CTZ center as well. Clear all of you? Now, moving on further. We will look into one major example of emetics. Okay. So, under emetics we have copper sulphate. Under emetics we have copper sulphate. Copper sulphate, also known as cupric sulphate, also known as blue vitriol, has got a molecular formula of CuSO4. It has got a molecular formula of CuSO4. It occurs in pentahydrate form, which is .5H2O. Molecular weight of copper sulphate is 249.7 grams per mole. 249.7 grams per mole. Copper sulphate belongs to the category of emetics. How is this copper sulphate prepared? How do we prepare copper sulphate? Well, the preparation involves taking granulated copper in the presence of air, and reacting it with sulfuric acid. Copper in the presence of air or oxygen is made to react with sulfuric acid, H2SO4. So, this forms copper sulphate. Which is CuSO4. We balance the reaction. 2 molecules of copper reacts with 2 molecules of sulfuric acid in the presence of 1 molecule of oxygen. Forms 2 molecules of copper sulphate and water gets released out. Alright, basically a dehydration reaction where water is getting released out. 100 grams of copper are added to 100 ml of concentrated sulfuric acid. Alright, 100 gram of copper is added to 100 gram equimolar of sulfuric acid, concentrated sulfuric acid. The flask is heated and if necessary to complete the reaction, additional 80 ml of sulfuric acid could be added. Copper sulphate is obtained also from the residue remaining in the flask. The solution is treated with additional portion of water in order to fully dissolve the copper sulphate. It is again heated and filtered. The filtrate is allowed to crystallize and obtained copper sulphate is obtained in the form of pentahydrate. Could be additionally purified by recrystallization. What are the physical properties of copper sulphate? Well, copper sulphate exists in the form of deep blue crystals, granules or powder. Copper sulphate exists in the form of crystals, granules or powder. It is soluble in water and insoluble in alcohol. its aqueous solution is acidic and it gives blue-green color with litmus paper. Its aqueous solution is acidic and it gives blue-green color with litmus paper. Clear all of you? The molar mass of the anhydrous and the pentahydrate form. The molar mass of the anhydrous and pentahydrate form of copper sulfate are 159.609 grams per mole and 249.685 grams per mole respectively. Anhydrous copper sulfate has a grey, white, powdery appearance. What is the appearance of copper sulfate? It is grey, greyish white, powdery appearance, whereas the pentahydrate has a bright blue color. The pentahydrate form has a bright blue color. The density of the anhydrous and pentahydrate forms are 3.6 grams per cubic meter is the anhydrous density and the pentahydrate form density is 2.286 gram per centimeter cube. Looking into the physical properties. Looking into the physical properties of copper sulfate. As we've just told, the pentahydrate form of copper sulfate is bright blue in color. It is bright blue in color. Alright, this is the pentahydrate form. Now, both hydrated and anhydrous copper sulfate tend to decompose on heating. Hence, do not have exact boiling points. Anhydrous copper sulfate has an orthorhombic crystal structure, whereas the pentahydrate forms have triclinic structures. It looks something like this. It has triclinic structure. The copper ions, now looking into the chemical properties. The copper ion present in copper sulfate react with chloride ions belonging to concentrated hydrochloric acid, leading to the formation of tetrachlorocuprate. Okay, copper react with chlorides or concentrated hydrochloric acid to form tetrachlorocuprate. Tetrachlorocuprate. Okay. Other chemical properties which we could discuss is, when heated to 65 degrees Celsius, copper sulfate undergoes decomposition reaction. When heated at a high temperature, that is to 65 degrees Celsius, copper sulfate undergoes decomposition to yield cupric oxide and sulfur trioxide. Cupric oxide and sulfur trioxide upon decomposition reaction. Copper sulfate is highly soluble in water. The solubility varies from 1.055 molal and 1.502 molal at 10 degrees and 30 degrees respectively. Depending upon increasing in temperature, the molality or the solubility values differs. Copper sulfate can be assayed by iodometric titration, wherein copper sulfate, iodometry as we all know is a two-step reaction. It is an indirect titration method. Copper sulfate is first made to react with potassium iodide so that potassium sulfate and cupric iodide is removed out. Potassium sulfate and cupric iodide is removed out. This cupric iodide is unstable and decomposes to cuprous iodide, Cu2I2. It decomposes with cuprous iodide and iodine. This iodine is treated with standard 0.1 normal sodium thiosulfate solution. This formed iodine is titrated. It is titrated. Clear all of you? So, this iodine is made to react with sodium thiosulfate. Titration is continued until blue color disappears. 2 grams of potassium thiocyanate is added towards the end point. This converts the small quantity of cuprous iodide into cuprous thiocyanate and prevents the backward reaction. Now, each ml of 0.1 normal sodium thiosulfate is equivalent to 0.02497 grams of copper sulfate. Clear all of you? So, what has happened here? Copper sulfate is first made to react with potassium iodide. So, potassium sulfate and cupric iodide is formed. This cupric iodide decomposes into cuprous iodide and iodine. This iodine is titrated with standard 0.1 normal sodium thiosulfate using starch as an indicator. This titration is continued until stable faint blue color appears. or ceases, 2 grams of potassium thiocyanate is added towards the end. Why do we add this? This converts the small quantity of cuprous iodide into cuprous thiocyanate and prevents the backward reaction, so that the iodine which is already formed gets titrated with the thiocyanate. Alright, so that our end point does not get affected. Starch is used as an indicator here. Uses dose of 300 mg in 30 ml is used as an emetic. It is used as antidote in phosphorus poisoning. Thank you.